We're now starting a unit on circular motion. When you look at a circle, you can discuss several factors about the circle, and the most important one is the distance. If you have an object around about here, it travels a certain distance around the circle, which is described as the arc length mathematically. And since if you were trying to determine that arc length, you might look at it as in terms of a ratio. So for a full circle, you'd have to travel 2 pi r around the circle. And so the ratio of that arc length over the full circle is that equivalent. And that is equivalent to the angle that it travels compared to the full angle of the circle, so 360. If you rearrange these two equations, you can end up with a expression for the arc length of s equals 2 pi r. And we'd normally have this on 360. 2 pi r theta, I think. But if you use theta in radians, then you can have that as just 2 pi r theta. We're mostly going to ignore looking at angular velocity and using radians, so we're going to focus mostly on linear velocity. When we have an object that's travelling at a constant speed around the circle, it will cover that entire circumference. So before we were talking about the displacement, but we also know that velocity is the change in displacement over the change in time. So if we're looking at change in displacement, we say, well, let's find out how long it is around the whole circle. Then again, we're looking at 2 pi r. And we use the term of t period, which we saw in simple harmonic motion, in the same description here for time. And that's because t is basically a period of revolution. It can also be stated as revolutions per minute or RPM, and also sometimes stated as rads per second. That's our velocity. One of the important things is this is just an example of simple harmonic motion. So if we start off at this position here, then we're going to go to a maximum away from that position. I'm going to go to a position here and then back again to here. So it is an example of simple harmonic motion. Just to go over that period and frequency of rotation, the period is the time for one complete revolution. And if you use angular velocity, then it's just 2 pi over r. We're not, we're using just linear velocity, so it's 2 pi r over v. And again, the frequency is just the inverse of that, so v over 2 pi r. These are important things to remember because you can use them in other equations. So for an example, if you have an object that travels in a circle, radius 15 meters, and it has a velocity 10 meters per second, how long does it take to complete a circuit? Well, the time taken is equal to the distance over the speed, or the circumference over the speed. In our case, 2 pi times 15 divided by 10. Work it out on your calculator, 9.4 seconds. Now, if we have a constant velocity, then we would normally not have acceleration. But when we've got these sorts of things, we can have acceleration. Because it's a vector quantity, you can have a magnitude and a direction. And so your objects can accelerate in any of these ways. There's 3 ways. One is constant direction and changing the speed. So that's when you're speeding up or slowing down in a car, for example, which is linear acceleration. Or you can have a constant speed, but be changing direction. And this is what happens when you have circles. Or it can change in both speed and direction. And that's when it's going to have angular acceleration. Angular acceleration we're going to come back to when we're looking at non-uniform circular motion. But uniform circular motion is this one here, uniform. And our acceleration can be defined by v squared on r, so our tangential velocity squared divided by r. And there's a little derivation that you can do for that. The centripetal acceleration is in addition to any tangential acceleration. So any motion in a curved path has a velocity that's constantly changing. And so as it goes around, you've got velocity here, velocity here, velocity here. Your direction is constantly changing. And because of that direction, you end up getting an acceleration. If you have an acceleration, you get a force. So that centripetal acceleration gives you centripetal force, and the magnitude of the force can be determined simply by F equals ma, Newton's second law. But our acceleration, as we saw before, is v squared on r. So our centripetal acceleration is mv squared on r. The direction of this force, remember force is a vector, is always inward, but it's constantly varying. It's always inward, but of course, as you've got your circle, sometimes it's inward here, sometimes it's inward here. So, just to summarize, this is our linear velocity, which is 2 pi r on the period, centripetal acceleration, which is v squared on r, and centripetal force, which is mv squared on r. The total acceleration. Now this is when you have non-uniform circular motion. If the speed is increasing or decreasing, then you get a tangential component in addition to your centripetal acceleration. So first you have your centripetal acceleration and your tangential, and then you can use vectors to find out what is the total acceleration. Just to describe the differences between uniform and non-uniform circulation. Uniform circulation is always at a constant speed. I don't say constant velocity, constant speed. But if you're talking about angular velocities, which is looking at speed and acceleration in an angular or rotational frame of reference, then you'd have constant angular velocity. But we're mostly just talking about constant speed. Non-uniform circular motion has changing speed. So it's speeding up or slowing down, which means it's accelerating or decelerating. So this is this one here, which means that you're going to have a tangential acceleration as well as a centripetal acceleration, which will give you a total acceleration. So you might have come across the term centrifugal force. We don't use it because it can become confusing. The centripetal force is the force that must be applied to force an object in a curved path. But the centrifugal force is not really a force. It's kind of considered an effective force, and it's just used to explain the behavior of objects which are in a frame of reference that is rotating. So the example we have is you're driving along in your car and you've got your mobile phone sitting on the bench next to you. As you go around the curve, the mobile phone starts moving off away from you and you're like, no, come back, come back. It's not moving. Because you're moving in this circular frame of reference, going around this curve, the object, it just wants to keep going straight with the initial velocity that it had. So you can see from this diagram, this is the initial velocity of that object. It's trying to keep going straight, and so as the car curves, it keeps going straight. The way that we talk about this is we can talk about centrifugal force. I prefer not. I would rather think of it as the object is continuing to move in the same rate as what it was before. So it's continuing to move in that direction because there's no other forces on it. And basically that's because the friction of the seat or the dashboard is not enough to keep those objects on that curved path. We'll come back to the frictional force later when we have a few examples.